Yeah, now we add a delay, or we calculate the algorithm in the case of a real algorithm. Now we add a delay of d is 1. So we draw no new signal block diagram, which looks like here my new DB controller, and here is a delay, 1 sampling time, and here is our process, again with 3 0.5 and negative feedback. Here is control difference, desired value, process output. Here we have the y value, and say this is y delay. Now now it is, for the controller, it is absolutely the same as if the delay is hidden in the controller algorithm or the delay is hidden in the process algorithm. So we can say, okay, green case, this is the real algorithm, or the blue case is the same. This is a delayed process. I think I should go back in the document to tell you again what a real algorithm is, because this I think it could be helpful now in this case. So I open the paper with this relevant. On page 20 in the paper, on the page 20 we have shown that there are 2 cases of algorithm. The ideal algorithm, the output of the calculated yn of this algorithm comes at once after calculation to the DIC. So I have a delay in my control algorithm from ADC over calculation time to DIC, just hardware dependent. And if I shift the position of the source code line output now to the beginning before I calculated it, then this contains the value of the last calculation. So this is 1 complete sampling time ago. So now I have a delay, an artificial longer delay, independent of the hardware, just of 1 sampling time. Yeah, the real algorithm makes my algorithm independent from the conversion time of ADC, independent of calculation time of this line, independent of conversion time of the DIC. Here this delay is exactly 1 sampling time, so the D, in our case, the D is 1. So sometimes the real algorithm is better if this is not neglectable. The delay of the hardware is not neglectable. Okay, back to our example. And now there is a delay here, and we have seen that the algorithms now are different. We can say, okay, the in black, the X output of N now is, we can copy this line, is 0.8187 times old output plus 0.5438 times the input, which is now a yd of n-1. yd of n-1. Now that is the input of my unchanged process. We know that y of d n is y of n-1. That is a delayed output of my controller, and my controller algorithm now has to be written in yn is, so I have to go back to the situation where I described this. Now d is 1, independent of this d is in the numerator or in the real algorithm, in the process. This z to the power of minus d could also be a part of the controller. In the numerator we have a delay, independent if this is a process or the controller, and then in the denominator of the controller we have now to change the z to the power of minus 1 to z to the power of minus 1 minus d, in our case minus 1, this is minus 2. So the P1 now is multiplied with z to the power of minus 2. That means my algorithm now has to be written as y of n minus 2 plus q0. What was q0? 1839 plus 1839 x control difference n minus 1.505 x d n minus 1. That is, now the change is only this point, that we here in our algorithm have now 2 delays. There is a 2-step delay of my signal. Okay, let's work through the signals. I think the same what we can do is this example now gets similar, but in some positions different cases. Again, if you want to see the unit step response, so the input should be 1, constant 1, then we have the output x of n of the process. The control difference can then be calculated, and if I have the control difference I can calculate the output yn, and of course I can make a line which is yd of n, that is the delayed y signal. Okay, let's do the first step. N is 0. In this case we see a unit step at my desired input. X of course is not changed in this moment, so there comes nothing back, so xd gets the full power step function. Here's 0, and the step function goes directly through the summing point to the input of the deadbeat controller. Y of n is now 1.839 times 1, so this is unchanged 1.839, and the one delayed output is of course 0. So the first line is without any calculation, so let's just go to the situation 1 sampling time later. The desired value is still 1. X, you see yd is now the input of my process. If this is 0, then of course output cannot change, so x in this situation is again, x1 is again 0. xd stays at 1, unchanged, and now we calculate y of n. Y of 1 is what? Y of 1 is, this is still 0, plus 1839 times xd of 1, xd1 is this, is 1, minus 1.505 times xd of 0, and xd of 0 is also 1. and we know this result. This is this 0.333 period. So we have our signal y of n is 0.333, and yd of n is now this signal, of course, the value 1.839. So we can now go over to the third row in my table. What happens in this situation? Now xd is constantly 1.839. That means we know from the situation before the result of x2 is 1. I prove it by calculation of x of 2 is, here this line, x of 2 is 0.8 times x of 1 was 0, is 0.5438 times xd of n minus 1. N is 2, and the argument here is 1. xd of 1 is 1.839, and you can believe me, this is exactly our 1. xd of 2 is now 0. Y of 2 can be calculated. Y of 2 is now y of 0. Y of 0 is 1.8 plus 1.8 times xd of 2. xd of 2 is 0, so this is 0, minus 1.505 times xd of n is 2, this is 1, xd of 1 in our table is this is 1. And you can also again believe me, this is our 1 divided by 3 value for my output. So this stays at 0.333, and this then is 0.333, and we can now calculate the same. We have the situation that x of 2, x of 3, what is x of 3? X of 3 is 0.81 x of 2. X of 3 is 0.8187 times x of 2 is 1 plus 0.5438 times yd of n minus 1. yd of n minus 1 in the situation 3 is 0.333. So this again is 1. So here in the case of 3 we have x3 still 1, then this is 0. Y of 3 now is y of 3. xd 3 is 0, xd 2 is 0. We have only yn is the old output 2 steps before, and this is 0.333 because this value is 0.333. That's all we can say. Y of 3 now is 0.333, and now in the next lines there is no change in all values, so we are ready. And the curve we get is just blue curve and red curve, just one step shifted to the right side. Yeah? The blue curve and the red curve are identical, but the whole signal behavior is shifted one step to the right side. T and this is 0.1, 0.2, 0.3 seconds. N is 1, 2, 3, and the blue curve is now just, and the red curve is just this. So you see we have a settling time 0.2 seconds. This is 2 steps. We have 1 step more in our situation if there is 1 delay, but the behavior is unchanged, is exactly the same. Okay, so far. Now some words to a second version. Second version of deadbeat controller. This version is called deadbeat with an index, say V or nu or what you say, means ready after new steps if nu is process degree. The second version is called deadbeat nu +1 because this controller is ready after m+1 steps. So he needs 1 step more than the original deadbeat controller, with an advantage. The first impulse, that is the most dominant impulse here, the first impulse has a smaller amplitude. First pulse has smaller amplitude. Let's look into the paper and then we make our example. Yeah, paper. Okay. Yeah, here in chapter 9.3.1 we have this second version of a deadbeat controller. The idea is that the large Q, E0, which defines the first amplitude of the previous deadbeat controller, is now put on 2 steps. Yeah, we can say, okay, there's a blue curve. You can say deadbeat nu +1. We assumes that the diagram have the following diagram. The idea, just to show you the idea, not this large, but now we take 2 steps, say this, and finally 0.33, so that the power of this impulse is the same. The length is doubled. That means the amplitude goes down. How large this amplitude is, we can define. If we make this smaller, then imagine that this will be higher. Or if this will be higher, then of course this will be lower. It depends on the choice of the first amplitude, the first Q0, and that is the idea. So look into the paper. This Q0 is a free choice. The letter A here is the original, the old Q0. 1 divided by sum of the b's was the Q0 of my last calculation. Yeah, look for this. That is the original Q0. Now we have a new one, a free choice. Of course, this Q1 could not be larger than this, but can be smaller. And the limits of the choice of Q0 are defined here on the next page. Qmax is our original one, could not be larger, and Qmin can be calculated with this expression. And the Q0 can be between Qmin and Qmax. Yeah, if R, the new parameter between 0 and 1, could change now the Q0 value between both these values. If R is 1, this is 0, we get Qmin. If R is 0, we get here a 1, and then we have Qmin minus Qmin plus Q max, then we have the original one. So this is a selection of with a letter between 0 and 1, the choice of the Q0, the new Q0 of my new version. Let's make an example. You see, okay, if I have chosen my Q0 here, then the calculation is a little bit different, yeah, but just changed equations with some, yeah, with this original Q0 and this new Q0, you see that is not really more complicated. The calculation takes a little bit more steps, but can be done, of course, with the computer in milliseconds. Yeah? Let's do an example with our previous controller. So, example. Process is the same. Process unchanged. We know the original Q0, or in our case the A, is 1 divided by B1 is our Q1839. Is 1839. Now we calculate that this Q max, yeah, is 1.839, and Q min, or Q0 min, we can say Q0 min, is 1 divided by 1 minus A1, 1 minus A1 times B1. In our case, this is 1 divided by A1 is negative, so we get 1 point A1. Where is A1? A1 is here. It's negative 0.8187. So we have 8187. Yeah? 0.8187 plus 1 is 1.8187 times our B1, and B1 was forgotten, sorry for this, 0.5438. 0.5438. And this is, okay, this is, the result is 1.011. I select selection. I want to have a very small new Q0, so I select R is Q min, R is 1. R is 1. That's what I want to know. R1. So Q0 new is Q0 min is 1.011. Now we go through the equations to calculate the other new Qs. I copy the equations. Yes, we need for this the A1 was negative 0.8187 and B1 was 0.5438. Then we have Q1, which is our new Q0, Q0 new times A1 minus 1 plus A, and A was this value, and you see what happens. This becomes a 0. But now there is a Q2, so we have more multiplications. Q0 new times now my problem is A2 minus A1 is the equation, plus A1 times capital A is, okay, there is no A2, that is only valid, so this is Q0 nu is 1.011 times negative A1 is negative 0.8, so positive 0.8187 minus A1 times A minus A 0.8187 times original A 1.839. The result is negative 0.6778. There is no other Q, then we have a P1, which is Q0 nu times B1. In our case, this is 1. Uh, 1.011 times B1. B1 is 0.5438. So this results in 0.5498. And there is a P2, which is Q0 nu times P2, B2 minus B1 plus B1 times A. This, of course, is 0. No, this was also 0. So this is 1.011 times negative B1, negative 0.5438 plus B1 0.5438 times A is 1.839 gives 0.4502. Okay, and other Q's, all other Pi, Qi are 0. Okay, so this is the algorithm, and the question is, of course, what happens now with my signals? I think we should see this with Windy at C# in my simulation program, which of course can more easily calculate this result, but of course we can also could do this manually in the same way that we have done before. Okay, this will be in the next video.